From the earliest days of human civilization, we've sought to understand the world around us. Our ancestors, with their rudimentary tools and keen observations, began to notice the regularities and patterns in nature. They saw the cycles of the moon, the changing seasons, and the predictable rise and fall of the tides. We looked to the stars, mapping their movements across the night sky. Early astronomers meticulously charted the constellations, seeking to understand the heavens and their influence on our world. We observed the rivers, noting their flow and the life they sustained. The trees, with their growth rings, told stories of years gone by. Every element of nature seemed to hold a secret, a pattern waiting to be deciphered. We craved to make sense of the patterns, the cycles that governed our lives. Ancient records show our ancestors' attempts to document these observations, creating early mathematical diagrams that laid the foundation for future discoveries. The cycles of the sun and moon led to the creation of sundials and early calendar systems. These tools allowed us to measure time, to predict the changing seasons, and to plan our agricultural activities accordingly. And so, mathematics was born. It emerged as a powerful tool, enabling us to quantify and understand the world in ways previously unimaginable. Mathematicians of ancient times worked tirelessly, developing methods and tools to aid in their calculations. At its heart, math began as a tool for measurement. We devised weighing scales to measure the mass of objects, and other tools to measure length, volume, and time. These early instruments were crucial in our quest to bring order to the natural world. We used it to quantify our world, the length of a day, the weight of a sack of grain, the distance between two villages. The abacus, one of the earliest counting devices, revolutionized the way we performed calculations, making it easier to handle larger numbers and more complex operations. The length of a day was measured using sundials, which relied on the position of the sun's shadow. These early timekeeping devices were essential for organizing daily activities and coordinating communal efforts. The weight of a sack of grain was crucial for trade and sustenance. Accurate measurements ensured fair exchanges and helped in the management of resources, which was vital for the survival of early communities. The distance between two villages was mapped out, facilitating travel and communication. These early maps were not just practical tools but also symbols of our growing understanding of the world around us. Numbers became our language for describing the physical world. They allowed us to record and communicate complex ideas, to share knowledge across generations, and to build upon the discoveries of those who came before us. This quest for quantification led to remarkable advancements. We built pyramids, charted the seas, and predicted the seasons. The construction of the pyramids, for instance, required precise mathematical calculations and an understanding of geometry that was far ahead of its time. Math, it seemed, held the key to unlocking the universe's secrets. It provided a framework for understanding the natural world, for making predictions, and for solving problems that once seemed insurmountable. But as our mathematical language grew, so too did the challenges we tackled. Mathematicians began to explore more abstract concepts, delving into areas that required new ways of thinking and innovative approaches. We encountered problems that pushed the boundaries of our understanding, problems that seemed to defy solution. These challenges spurred further innovation, driving the development of new mathematical theories and techniques, problems that seemed to defy solution. Yet with each challenge our understanding deepened, and our ability to quantify and describe the world around us grew ever more sophisticated. The journey of mathematics is a testament to human curiosity and our relentless pursuit of knowledge. One such problem emerged from the depths of algebra: the cubic equation. This mathematical beast, with its x-cubed term, seemed insurmountable. For centuries, mathematicians wrestled with it, seeking a general solution, a formula that could unlock its secrets. The challenge lay in finding a method to find the unknown x in any cubic equation. Squares were easy, we had formulas for those. But cubes? They seemed to mock our attempts with their complexity. This was no mere academic pursuit. The cubic equation held the potential to revolutionize fields like engineering, astronomy, and physics. But its solution remained elusive, a tantalizing enigma that captivated the greatest mathematical minds. The prevailing belief was that a general solution to the cubic equation was simply impossible. It was a problem that seemed destined to forever haunt the world of mathematics. For centuries, geometry reigned supreme in the world of mathematics. It was the cornerstone of mathematical thought, with its roots tracing back to ancient civilizations like the Greeks and Egyptians. These early mathematicians used geometry to understand the world around them, from the pyramids of Egypt to the intricate designs of Greek temples. Geometric proofs, with their elegant diagrams and visual logic, were the gold standard. They provided a clear and intuitive way to understand mathematical relationships. The beauty of geometry lay in its ability to visually represent complex ideas, making them accessible and understandable. Algebra, with its abstract symbols and equations, played a secondary role. It was seen as a tool for solving specific problems rather than a fundamental branch of mathematics. Algebra was often considered less intuitive and more difficult to grasp because it lacked the visual appeal of geometry. But the cubic equation demanded a new approach. The limitations of geometric methods became apparent when mathematicians tried to solve these more complex problems. The cubic equation, with its higher degree of complexity, could not be easily represented or solved using traditional geometric techniques. It forced mathematicians to break free from the constraints of geometry and embrace the power of algebra. This was a significant shift in mathematical thinking. Algebra offered a new way to approach problems, one that was not limited by the need for visual representation. This shift in perspective proved to be a pivotal moment in mathematical history. It opened up new possibilities for exploration and discovery. Mathematicians began to see the potential of algebra to solve problems that were previously thought to be unsolvable. Think of it like this. Geometry is like building with blocks. Each block represents a specific shape or relationship, and you can see how they fit together to form a structure. This visual and tangible approach makes it easier to understand and manipulate. You can see the shapes, the relationships, the structure. It's like constructing a building where each piece has a clear and defined place. This clarity is what made geometry so appealing and effective for centuries. Algebra, on the other hand, is like working with a secret code. Instead of physical blocks, you have symbols that represent numbers and operations. These symbols can be manipulated according to specific rules to uncover hidden relationships and solutions. You manipulate symbols according to specific rules, revealing hidden truths. This abstract approach allows for greater flexibility and creativity in problem solving. Algebra can handle more complex and abstract problems that geometry cannot easily address. This separation of algebra from geometry was a bold move. It required a shift in mindset and a willingness to embrace new methods and ideas. Mathematicians had to let go of the familiar and venture into the unknown. It allowed mathematicians to explore new realms of thought, to develop new tools and techniques for tackling complex problems. This evolution in mathematical thinking led to significant advancements in various fields, from physics to engineering, and it paved the way for a truly revolutionary concept: imaginary numbers. These numbers, which cannot be represented on the traditional number line, opened up entirely new areas of mathematics and science. Imaginary numbers have applications in fields as diverse as electrical engineering, quantum physics, and complex analysis. Today, the legacy of this shift from geometry to algebra is evident in the tools and techniques used by modern mathematicians. Computer algorithms, advanced software, and abstract mathematical theories all owe their existence to the foundational work of those early algebraic pioneers. In classrooms around the world, students learn algebra as a fundamental part of their mathematical education. They are taught to see beyond the visual and to understand the power of abstract thinking. This education prepares them to tackle the complex problems of the future. The journey from geometry to algebra is a testament to the ever-evolving nature of mathematics. It shows how the field adapts and grows, constantly pushing the boundaries of what is possible. This journey continues today as mathematicians build on the work of the past to explore new frontiers. From the ancient Greeks to modern-day mathematicians, the quest for knowledge and understanding drives the field forward. Each generation builds on the discoveries of the previous one, creating a rich tapestry of mathematical thought that spans centuries. As we look to the future, the possibilities for mathematical discovery are endless. The shift from geometry to algebra was just one step in a long and ongoing journey. Who knows what new breakthroughs await us in the years to come? The very name imaginary hints at their controversial nature. Imaginary numbers, a term that evokes curiosity and skepticism alike, have a history as rich and complex as the equations they help solve. These numbers, with their square roots of -1, seem to defy logic. For centuries, mathematicians grappled with the concept, questioning how such numbers could exist within the realm of mathematics. After all, how could a number multiplied by itself result in a negative value? This paradox puzzled the greatest minds of the time, leading to heated debates and intense scrutiny. Yet, as mathematicians delved deeper into the cubic equation, they stumbled upon a startling realization. The solutions to these equations often required stepping beyond the boundaries of real numbers. These imaginary numbers, these seemingly impossible entities, held the key to unlocking the cubic's secrets. They provided a new dimension to mathematical solutions, one that was previously unimaginable. It was a concept that challenged the very foundations of mathematics. The introduction of imaginary numbers forced mathematicians to rethink their understanding of numbers and their properties. Numbers, it seemed, were not limited to the realm of the tangible. They could extend beyond the familiar into a realm where the impossible became possible. This new perspective opened up a world of possibilities. They could extend beyond the familiar into a realm where the impossible became possible. Imaginary numbers became a bridge to new mathematical territories, allowing for the exploration of concepts that were once deemed unattainable. This realization didn't come easily. It was a journey fraught with challenges and opposition. Many mathematicians were hesitant to accept the existence of such numbers. It was met with resistance, skepticism, even outright dismissal. The mathematical community was divided, with some viewing imaginary numbers as a mere mathematical trick, while others saw their potential. But a handful of courageous mathematicians dared to explore this uncharted territory, forever changing the landscape of mathematics. Their persistence and vision paved the way for future generations. Their journey would lead to a profound shift in our understanding of numbers and their relationship to the universe. The acceptance and integration of imaginary numbers into mainstream mathematics marked a turning point in the field. It was a journey that would ultimately pave the way for some of the most important discoveries in modern physics. Imaginary numbers became essential tools in the development of theories and models that describe the fundamental nature of reality. In electrical engineering, for instance, imaginary numbers are used to analyze and design circuits. They help engineers understand the behavior of alternating current and the impedance of electrical components. In quantum mechanics, imaginary numbers play a crucial role in describing wave functions and the behavior of particles at the quantum level. They are integral to the equations that govern the strange and fascinating world of quantum physics. In signal processing, imaginary numbers are used to represent and manipulate signals, enabling advancements in communication technologies and data analysis. The seeds of this revolution were sown by those early pioneers who dared to think beyond the conventional. Their legacy lives on in the countless applications of imaginary numbers in science, engineering, and technology. As we continue to explore the frontiers of knowledge, the impact of imaginary numbers remains profound. They remind us that the boundaries of human understanding are ever expanding and that the impossible can indeed become possible. The journey of imaginary numbers is a testament to the power of human curiosity and the relentless pursuit of knowledge. It is a journey that continues to inspire and challenge us to this day.